Hi, today I want to show the procedure of designing bolts for a hydraulic cylinder to keep the sealing. Through that, first I need to find the pressure acting on the hydraulic cylinder, and I have a very simple example here. I have a very simple loading which is being generated when the excavator is lifting itself up. To find the forces, I can go here. I have two sliders cylinders, and I already made bushings in the top, so the sliders are sharing the load properly according to their stiffness. So here I can extract the loads by clicking on the joint that I'm interested in and then finding the relative force. To see the coordinate system, I can double click and check the vector again. So as you can see, the Z axis or Z direction is what we're looking for. So here on relative forces, I click on Z, and this is the force acting on the piston of the hydraulic cylinder. And as we play, we see that there is a spike which is happening because the boom is actually falling for the first time step before it converges. Then it converges to some positive number because the boom is being held by the hydraulic cylinder in the beginning. Then it switches to a negative value because now the cylinder is pulling the boom down and lifting the excavator. Now to calculate the pressure, here I need to find the axial force that I'm already doing and then basically divide it by the piston area to find the total pressure being generated inside the hydraulic cylinder. Next, we're going to use that pressure to calculate the preload or clamping force needed to be generated from the screws. So here I can right click and use the peak probing mode to find the maximums. And if I go back here, I have three maximums. The first one is when the solution is actually converging. And here we have convergence, and the maximum between these two is what I'm looking for. So I'm going to use this force to calculate the pressure here, as you can see. That's my force, and the piston area is shown here. And I'm going to have 23 megapascal of pressure inside the cylinder. Now I can use that pressure to find the clamping force needed to keep the cylinder sealed. Here you see how I use N factor and Y factor for the gasket. You can extract these factors from the data sheet of the gasket you want to use. Basically, the N factor is being used to show how much force you need to maintain the seal, and Y factor is the minimum force you need to keep the gasket flat while there is no pressure. So here you see that the required sealing force is being calculated by using the N factor, and both pressure inside the cylinder and also blowout pressure that is acting on the gasket itself. So here I calculated the basic sealing force that I need, and then based on the method that you use to fasten the screws, you should modify or correct the load that is being applied. I have this table from ASTM standard, and I'm going to just use torque range as example, and you can see that there is a plus minus 25% accuracy for a torque wrench if you're using torque wrench to fasten the screws. So I need to calculate both. I increase it for 25%, and this is the load that I'm going to use as the preload for the bolts. And usually you want to have the minus 25% as well. You just use this for checking, and this should be bigger than the force that is being applied, and it's a lot bigger than this force that we have as axial force. So even with reduced 25%, we see that the bolts are still maintaining the seal. Now let's go back. We're going to apply this axial force in the system and apply this force into the preload and run the calculation. Before I make any changes to the assembly, I need to make a wavelength from the parts that I want to simulate. So I'm not going to modify the actual part. And then I can hide the assembly and keep the parts that I want to work on. So I'm gonna apply, I'm gonna first model the bolts, and then I'm gonna apply the clamping load as preload. Then I'm going to apply the force coming from the hydraulic cylinder on the top part. So let's make a new FEMA simulation. I'm going to have all visible parts and click OK. Here my focus is on the bolts only, but if you're interested in calculating the gasket, you need to go with the nonlinear simulation and define a gasket material. Here I have a lot of circular shapes, so I'm gonna go with the higher order of tetrahedral mesh. I'm gonna select all the parts and go with around half of the recommended value. So I have the mesh now, so we can move to the simulation and applying constraints and loads. First, I need to apply contact. Since I don't expect the contacts to separate, I can actually use surface-to-surface gluing, so the simulation won't fail if the parts are separating. Now I want to have all parts glued together. Here you should have two pairs, as there are two pairs between the gasket and lower part and the gasket and top part. And you can see that the contact is defined here now. And then I'm gonna have a fixed constraint on the lower side. Let me hide the mesh and use the polygons. I'll fix the lower body, and then we want to apply an axial load. Go with the force. The force is being applied here, and the vector is upward. I can use this type to apply the load, and we already have the load here, the axial load. Next, I need to define the screws and apply the preload. So let's activate the meshing, and here I want to have a bolt connection. I have a bolt-in tapped hole, and I can use this as a smart selector to select all the bolts in the simulation. and I have dimensions here. So the hole is 16, so I'm looking for 8 as radius between 5 and 10 on this part, and then we run and it automatically finds 28 circular edges that we want to select. Click OK. I only need the top ones, so I just hold shift and deselect the rest of it. End up with 14 edges selected as the head of the bolt. And now I have to increase that diameter because of the washer face. The washer face, as shown here, is 25.5 in the top, and that's what I have here as the diameter. So NX is going to expand the spider elements to this size. And on the other side I have the tap surface. Here I can actually hide this, and also the gasket, which I don't need. I again use the smart selector to find the circular faces now. Same diameter I want, and on this part I run the small selector and it will automatically select 14 faces for me. So here I have the faces that are threaded, and the total bolt length I have here as 140. So I'm gonna have 140, and effective thread length is only this part of it, which is 70. I'm gonna leave some space because we don't expect the engagement all over the threads. For safety, I'm gonna leave 5 millimeters. And I want to have C-bar elements. The load is being distributed by rigid body element 3. All the options are okay, so click OK and it will generate the bolts here, as you can see. So the head of the bolt is presented by this spider element in a 2D plane, and the threaded side that is engaged is shown with this 3D spider element, and these lines are representing the shank of the bolt. Now I can define the materials that I'm going to use especially for the bolts. So I'm going to move to the bolt. Here we go to edit. Since I'm using a C-bar, I need to define a section for it. And I'm using a M16 because the diameter here, as you can see, is 16 millimeters. So I need a section with the radius of 8 millimeters. And click OK. And then for the material I want to use is the highest grade of the bolts I can have, which has the minimum proof strength of 970 megapascal. This I couldn't find in default materials, but we can make a copy of one of the materials and modify it and then use that for the screw. So here I'm going to copy that steel and use these values. So let's say steel 12.9, and then under strength I have yield strength. I'm gonna use the proof strength as yield strength. The yield strength is going to be a little bit lower than the proof strength. So 970 megapascal. This is in kilopascal, so make sure your units are correct. And 1220 as the ultimate strength. All the other parameters are okay. We are using steel, and the original material was steel as well. So I'm going to use this material for the screws. There isn't any non-structural mass. This is a mass that is not working in any structural load, meaning like a washer or some extra material that you're going to have on the screws. For the flanges, also going to use a steel. So here we go to edit. I'm going to use this steel for the flanges. Now I have defined the materials and loads. I can move to simulation to apply preload to the bolts. Let's hide the polygons. I only want to keep the 1D elements, which are representing the bolts. Here I go to load and bolt preload. We already calculated the preload here, and this is the total clamping load, so I have to divide it by 14, and I select all the bolts and click OK, and you're going to see that this icon shows that the preload is now being applied on the system. Let's save here and run the simulation. Now the simulation is finished. Let's take a look at the result. As I said, I'm interested in the axial stresses on the bolts, and here we can see that the stresses on the bolts are almost the same. The maximum is around 1400. Here, as you see, the tensile strength is around 1220. So this shows that the screws are failing, and we can either increase the size of the screws or use a bigger flange to reduce the stress on the bolts. At the same time, I can take a look on the flanges as well to make sure if the stress is within the range of the allowable stress for the flange material.